Hi, how to solve some PDEs and how to use the chain rule to solve some PDEs. What are first PDEs? PDEs are partial differential equations. So these are equations where the variable is a function f and it appears in the equation as itself f together with its partial derivatives with respect to all the variables x, y, z, etc. Now, in this video, I will show how to solve some very basic PDEs and also how to use the chain rule to solve some a little bit more complicated PDEs. So first, let me recall the chain rule. These formulas were introduced in the previous video about the chain rule. Then I will take a first example where I take a very simple PDE. It's a partial differential equation where the function to find is f, which is a function of two variables x and y. It's a C1 function and it satisfies df over dx equals to x2 plus xy2. So it's like saying, can you find a function f whose derivative with respect to x is equal to x2 plus xy2? So somehow it's also finding a primitive to this function with respect to x, right? So in this case, what's the primitive of x2 with respect to x? That's x3 over 3. What's the primitive of xy2 with respect to x? That's x2 over 2y2. So f can be written as x3 over 3 plus x2 over 2y2 plus eventually a function of y that can be a constant or really a function of y. Why? Because when we differentiate f with respect to x, this function of y will disappear. Its derivative with respect to x will be equal to 0. Let's take another example now where the function to find f is also a function of two variables, but it's a C2 function because it appears in the equation as differentiated with respect to x and to y. So it's the second derivative. So we need to find a function f whose second cross derivative with respect to x and y is equal to 0. So we write d2f over dx dy is equal to 0 and we start to find the primitive with respect to y because it's the second derivative. So it means that we need a function f whose derivative with respect to x is equal to a function of x because we need the derivative of this function with respect to y to be 0. So this function will depend only on x. That's why we say that df over dx will be equal to some function g of x. Then if we want to find f, we'll say then f will be equal to a function whose derivative will be this small g of x. So we say that f will be equal to a function of x which is big G of x, whose derivative will be equal to small g of x, plus eventually any function of y, because the derivative over x of any function of y will be equal to 0. So finally, any function f which is equal to a function in x plus a function in y, and of course these two functions should be, the first one, big G, should be twice differentiable and h should be at least once differentiable. So f will be equal to any function twice differentiable in x plus any function once differentiable in y. So now if you take any example, like if we take ln of x plus cosine y, it will work. Its second derivative with respect to x, y will be equal to 0. If you take ln of x over e exponential x plus, let's say, y cosine y squared over sine y, it will work as well. Let's take now another example that is more interesting because it contains a more advanced PDE. So it's a function f whose derivative with respect to x minus 3 times its derivative with respect to y is equal to 0. But in this case, they are telling us to use the change of variables u equals 2x plus y, v equals 3x plus y. So first, let's build the dependency table. F depends on u and v, u depends on x and y, and v depends on x and y. Now, what is the idea behind this type of exercises? The idea is to transform the PDE into a new PDE in terms of u and v instead of x and y. But the objective is to obtain another PDE in terms of u and v that is more simple to solve than the one we had in terms of x and y. So we need to find df over dx and df over dy in terms of df over du and df over dv using, of course, the chain rule, and then replace them in the equation to transform it into a new one in terms of u and v. So of course we'll use the chain rule. So the first formula is df over dx equals df over du over dx plus df over dv times dv over dx, which is equal to 2 df over du plus 3 df over dv. We do the same thing to calculate df over dy. It's df du dy plus df dv dy. That's df over du plus df over dv. We replace df over dx and df over dy in the equation, and we get 2 df over du plus 3 df over dv minus 3 df over du plus df over dv equals to x, which leads to minus df over du equals to 0. Now, minus df over du equals 0, that's easy to solve. It's like the one we solved in the beginning. So any function that depends on v will have its derivative with respect to u equals to 0. So f will be then a function of v. So that's g of v. That's why, finally, the function f of xy will be equal to any function of the package 3x plus y, which is v.